And the first one is Ioan Hadade. Ioan went through the different universities in the UK, from Surrey, from Edinburgh to Imperial College to Surrey to Oxford, and then he started at the European Centre for Medium Range Weather Forecast, ECMWF, where he is a principal scientist, and he's kind of leading the application team, HPC application team there. And whenever we are having trouble with kind of the model is not running fast enough or needs to kind of fit into some window, whether it's a physical model or the machine learning model, we would always kind of knock on Ioan's desk because he knows how to kind of do the magic and make the model run fast and efficient. So, Ioan, the floor is yours.
Thank you, Peter. Hello, everyone. I'm not going to introduce myself again, but I'm presenting here the work done on behalf of the whole climate DT team and the people at ECMWF. So I'm really standing on the shoulders of giants here, and I'm just the medium, and I'm hoping to do a good job. So we're going to dive straight into it. So first of all, what is Destination Earth? Destination Earth is an initiative by the European Commission aimed at building high-resolution digital twins of the Earth. And the reason for why we would like to do that is to be able to better predict extreme events and also simulate and try to adapt to the impact of climate change. And really, Destination Earth is an information system. It's an information system made out of different components. It is implemented by 3 entrusted organizations, ECMWF, ESA, and EUMETSAT. And each organization is responsible for their own bit in the system. So for example, we have the digital twins. The 2 high-priority digital twins that we implemented in the first 2 phases were the weather-induced extremes digital twin that looks at short forecasts to detect high-intensity extreme events and then run an on-demand, higher-resolution local forecast over the area to better predict and allow for emergency responses for these events. And then there's the climate change digital twin, that's the focus of this talk, which looks like multi-decadal simulations at very high resolutions to better inform policymakers on how to adapt to the ever-changing climate and the effects that we all feel. Except for the digital twin, there's the digital twin engine that's also implemented by ECMWF and its partners. And the digital twin engines, you could see the wheels on the left-hand side and then also on the right-hand side. This is the whole infrastructure that deploys the digital twins on Euro HPC supercomputers and also allows for users to interact with the data later on and also participate in the co-design process. We then have the data lake that's implemented by EUMETSAT, and this is where all of the data, once the simulation is run on the HPC, the data is then moved to a data bridge that usually sits next to the HPC from the fast parallel file system to long-term storage, and from there, the core platform that's implemented by ESA, that's what the users use to interact with the data via modern software stacks based on Jupyter Hub, etc. Now, digital twins, we talk about them all the time, and we know that as a short definition, it just means a digital replica of a physical system. And I would like to actually postulate and tell you that, in a way, us doing, all the people doing global weather forecasting, we've been kind of doing digital twins for a long time, and because we are modeling, essentially, the physical system day in, day out. And as an example, this is something new done by my colleague, Philippe Lopez at ECMWF. As you know, there was the Artemis mission recently in April that did a flyby around the moon. And there were a few photographs captured there of the Earth, both using a Nikon professional camera on the left-hand side and then also an iPhone 17 Pro Max on the right-hand side by one of the astronauts. And what my colleague tried to do is try to use the operational weather forecasting data from ECMWF at 9 kilometers to try to calculate the trajectory where the Orion spacecraft would have been at the time when the picture was taken and run forecast to see if they can predict exactly the same cloud structure as in the picture. And you can see here, both on the right-hand side in both pictures, on the top, it's actually, you can see 2 different forecasts with 2 different lead times. One is 1 day, so basically the point of intersection is 1 day into the forecast, and you can see that all of the structures are the cloud formations are very well resolved. And then there's another one that looks at 5 days, 5 days lead time. As you know, weather forecasts usually tend to degrade as the lead time increases, but even in that scenario, we are doing a pretty good job, bearing in mind that a lot of these convexity clouds are very unpredictable and hard to simulate. And if we go even further, we look at even higher resolution stuff, now captured with a very high resolution satellite imager, and another, as one example in this image, and another one is actually a simulation. So before I tell you which is which, I'd like to objectively think about which you think is real and which one is actually the simulation. And you don't have to tell me, but the left-hand side is the actual satellite, so if you wish, the ground truth, and then the right-hand side is a 2.8 kilometer simulation with our global IFS model. So you can see, and I hope I convinced you, that we are doing a pretty good job in terms of replicating a physical system in the digital world. So what is the climate change adaptation digital twin? Well, it's a new type of climate information system, and we use it to assess climate change and so we could help us with different adaptation strategies. And most importantly, the high resolution nature of it helps us to do this at local and regional levels, where the impact of climate change is most noticed. And the climate change digital twin is implemented by a consortium led by CSC and many partners there. You can see many supercomputers, supercomputing centers, well-established climate centers, and also, most importantly, we have the weather agencies in Europe that are crucial to help us tackle such a big mission. These are the partners that were involved in phase 1 and phase 2. We have recently started phase 3, and we also welcome our friends from Jülich and of course our friends from Meteo Swiss as well into the consortium. So the climate change digital twin, what do we actually do? So as I said, we're running multi-decadal simulations, so there are different types of simulations. We have what we call a control simulation, where we start from 1990 with the forcings that we have then, and we let the model drift naturally so that we can use this as a control to compare with all of the other simulations. We have an historical simulation where we start with from 1990, and then we apply all of the observations that we have and produce a 20-year forecast that we use to evaluate against existing observations to make sure that what we are actually looking at is correct and the predictions are accurate. And then we have the long projections, which uses CMIP scenarios for forcings, where we then see from 2020 onwards project into the future. A novel thing that's been included in the climate DT is what we call extreme event storylines. So these are what-if scenarios. What we do is we take an extreme event, a recent extreme event, and then we look into the past using the forcings that we have there to see what the effect of that extreme event would have been pre-industrial, in the pre-industrial times. And then we also model to see what would this event look like in a climate with plus 2 degree Kelvin temperature. So far, we've done more than 210 years of simulation at 5-kilometer atmosphere and 5-kilometer ocean. This is unprecedented. 135 years at 10-kilometer atmosphere and 5-kilometer ocean for the storylines, and we have accumulated more than 10 petabytes of data sets. And to show you a little glimpse, a snapshot of these digital twins, we've been running 3 leading Earth system models. We have running ICON, developed by DWD and MPI and Meteo Swiss, IFS coupled with a phase of motion model, and IFS coupled with a NEMO ocean model. And in this visualization, you can see some snapshots of this that shows different features in different times. For example, on the left-hand side, if you look at the ICON model, you will see that a hurricane is developing slowly and moving towards North America. If you look at an IFS NEMO, for example, you see 2 typhoons that are heading towards Japan in August 2038. And what I would like you to capture from this is really the high resolution allows us to model and really resolve all of these flows. This is why these models are also called storm resolving, because they allow for all these physical processes to emerge. And just another snapshot, when we look just at the ocean, for example, this is another simulation done by my colleague Andreas Müller, where he sped up the ocean currents because they move at a different pace to the atmosphere. He sped them up by 24x, so that you can actually see also the change in ocean currents and ocean temperature. The scales are used differently for that very reason as well. So you can see snapshots from the ICON ocean model, from the NEMO ocean model, for example, and then from IFS PHASM. Why is high resolution so important? I'm going to show you a qualitative example where on one side of the sphere is the 4.5 kilometer model that we run in the climate DT, and above is the traditional resolution that climate models run at, something like 100 kilometer. You can clearly see how the flow is resolved and interact with the orography, and this is what we mean by global simulation, but at local granularity, because you can now actually see the weather patterns and the structures in restricted areas, whereas before this was not possible. And another example, if we look at extreme heat, on the top-hand side, you see the leading regional models over the Alps areas. They are trying to calculate the mean annual maximum temperature from 1990 to 2005, as well as reanalysis. And then if we compare it with the traditional climate models at 100 kilometers on the left, and then with our models, you can see that we are actually capturing, and we are in good agreement with a very high resolution but regional model in a global model. And the same for the extreme rainfall. We can, over the Alps, which actually is an area due to the complex orography that's very hard to model. We can see on the top reanalysis and observations and regional models, and then at the bottom, you can see that our models are able to capture and model these very nicely. So why is high resolution so important? Well, it's important especially for small islands, right? Because that's where the impact of climate change will be noticed most, with rising sea levels, etc. And you can see in our example that compared to observations and also regional models, we are able we're in very good agreement with observations, and we're able to predict with a very good accuracy, which is really important. Now, I talked about what-if scenarios. This is an example, for example, of the storyline simulations. This is the Central European floods that happened in 2004. And you can see on the left, when we ran the model with the 1950 forcing, what the impact of this event would have been in terms of accumulated precipitations. And then in the middle, you see the event as it unfolded in 2024. And then when we actually applied the forcing for a +2 Kelvin temperature atmosphere, we can see that this event actually becomes, the intensity and the accumulated precipitations becomes much worse. So the climate DT workflow. So basically, if you look at the system architecture, you have the 3 models that are running on the HPC systems. They are all outputting the same data format to the parallel file system. This is what we call the field data object store. And from there, we have downstream applications that can consume the data as it's being written from the fast parallel file system. But also we can stream and we can do quality assessment as the model runs. After this, the data is moved to the data bridge, the data lake, and then from the data bridge to the data lake, and then users can also interact with it via the Destiny platform. And we run these models using workflows. This is done by my colleagues at BSc. And you can see, for example, on the left-hand side, you would have a simulation, and then this simulation would trigger a quality control, then a full quality control, then feed the data or notify the downstream application that the data is available, and they would then go and look at particular regions or particular the fields that they need for their own application. Running all of these on an HPC, sometimes you cry yourself to sleep. It's not always good. I mean, this example is one where you can see each job index there is basically a 2-week or a 1-month forecast. This is how we run for 20 years integrations. You run a 1-month forecast, and you write restart files, and then you start the next chunk. And you can see there the throughput of each chunk as it progresses. You can see dips where we had loads of issues maybe on the system with the interconnect or cooling, or we had a rack that went out because of cooling issues. So overall, the throughput was really good. We are talking about more than 180 or more than 230 forecast days per day in some instances. But this spans multiple months to run such a simulation. So it's not something particularly, it's a very long-term effort, and that's why you require complicated suites to make sure that you have all of the data at the end of the run, and to make sure that all of the data is correct. And for that, we use this Aqua real-time model evaluation. So as, for example, here the historical model runs, we are actually plotting and making sure that the results fit within the reanalysis, the ERA 5 reanalysis, and then we can also compare scores. Here, usually blue is good. This is why you should always know if you ever see this scorecard. So this is comparing with CMIP. And as I said, the data as it becomes available, we notify downstream applications that it's there, and then they can actually go and just look at the particular region or field that they want, the raw output, and then they could calculate their own derived variables. So for example, here's a one-pass algorithm that computes the distribution of weekly wind speeds. That's very useful for wind farms. One really great feature of the ClimateDT, which took a lot of effort from everybody, is the fact that all of these models output on the same grid. So all of these models have a completely different native grid, but in order for people to interact and all of these downstream applications to interact with the data, they need to have a common set of parameters and a common grid. And this is why we use the heel-pix grid. And this is done, for example, in the IFS model by on-the-fly I/O post-processing. We have I/O server nodes that receive the data from the model task, and they interpolate on the fly to the heel-pix grid and write this to the parallel file system. In this way, we can preserve and we can write both in the native grid and in the heel-pix grid, so we can compare in case there are any bugs or any issues. This is an example by my colleague Niels Vedig, how using just a Jupyter notebook, and thanks to the fact that it's the common grid, he can actually get, in this instance, the goal stream using in 2032, I believe, using all of the three models. He's going through creating a request using the software stack developed in the digital twin engine, and he's able to basically plot the exact same output from all of the three models and then compare them against each other. So I think this is something really powerful, and this is helped by the fact that we have a consolidated data portfolio, and also we are all writing on the same grid. It wasn't easy. You can start wars about data formats very easily, but I think we got somewhere pretty good in the end. And what we also do. And now, in the ClimateDT, this is my colleague Andreas. We are using this data, and we can build augmented reality. So this is an application that he developed for the Apple Vision glasses. You can use the iPad as well, and you can interact with the data, right? You can look at different variables. You can look at data at different times from all of the three models. This application is not yet released, but we're working on it, and hopefully it will be in the Apple Store very soon. What we've also done in the ClimateDT, of course, the resolution at the moment is 4.5 kilometers, but these models can go and can scale much further. We can see here, for example, we took Daniel from MPI and my colleagues from DKZ took the Icon model and ran them on the machines where the ClimateDT ran, the LumiG, LumiC, Mare Nostrum 5. In this case, Icon ran on GPU mostly, so they took that and scaled this across multiple resolutions, starting from 9 kilometers all the way to 1 kilometer, and also all the way to 1 kilometer coupled. And you can see that they got really good throughput and very good performance. The Icon model has very nice local communication, so it has a very good scaling characteristics as well in terms of weak scaling. And then we did the same with IFS. We used predominantly in this case the CPU partitions of both LumiC and Mare Nostrum 5. IFS is very efficient on CPUs. You can see that we got up to 97 forecast days per day on using the full Mare Nostrum 5 machine. And I want to thank Sergi and the colleagues for allowing us to do it. The weak scaling is not as good as Icon because IFS is a spectral model. And as you do weak scaling, the work per task is you can't really always get it to be at the right discretizations. For the IFS, we also started running on Jupyter now. We have a GPU adapted code using source-to-source translation tools because we want to maintain the same code. The scientists change the code all the time, so we want to make sure that we maintain the same code and the same performance on CPUs, but running on GPU. And here what I'm doing is, this is Jupyter is in early access mode, so there's still some issues to be ironed out, but I'm actually normalizing here the number of CPUs by the number of GPUs. That's the fair thing to do rather than comparing node for node because Jupyter has very fat nodes compared to LumiC and Mare Nostrum 5. You can see that at all of the resolutions we are outperforming the CPU, but the elephant in the room is energy efficiency. I mean, one Grace Hopper is 800, 900 watts. The Milan CPU on LumiC is something like 300 watts. So there's still a lot of work to do. We are in the climate community in particular, we have to be the first that make sure that energy efficiency is the most important or crucial aspect in our simulation. So there's still work to do. But even 1 kilometer using just 512 nodes, we have 51 forecast days per day. I know probably Daniel will show the great Icon results with, I think they had 150 forecast days per day on 5,000 GPU nodes. So we are getting we're getting a third of that at the moment. We're using 10 times less nodes. So I think there's progress also for us to push it and hopefully get to 1 simulated year per day on the full Jupyter machine with the help of Andreas and his colleagues. And the last bit, energy efficiency. I think here we are plotting basically the performance of IFS as normalized to megawatt hours. And you can see that on the y-axis is a log scale plot. And for the resolutions that we care about, the 4.4 kilometer on 256 nodes, this is pretty much where we ran the integrations. We're at 43 simulated days per megawatt hour. And as you go down to higher resolutions, you know, if you go to 1 kilometer, you're basically 40x of that. So this is why, in order for us to look at further resolutions, we need to make sure that we take energy efficiency into account. And I think that's the sweet spot. Around 40 forecast days per day per megawatt hour is the sweet spot when I think we can say, let's move to the next resolution for these climate models. And I'd like to end with one thing. I have 8 more seconds. I think when I joined ECMWF, as you know, ECMWF, we are formed by some member states, by European countries that 50 years ago said, let's all come together to do something together that none of us can do alone. And I think the ethos of that was the strength of a common goal. And this has been extended further with Destination Earth, where with the help of the European Commission and the EuroHPC and all of the wonderful partners that we had, we all tackled the main goal, you know, to predict extreme weather events and also to look at the impacts of climate change. And I think we should not forget this and look into the future with the same motivation to work together, because that's the only way we can tackle these important aspects that affect our daily life. Thank you.
Thank you very much. What a nice statement at the end. Are there questions? So there are 2 mics. There's one, and you can also post questions online if you want to. I don't have any questions so far. You will need to get up. Someone will need to get up and ask a question. Yes, there's one.
I have a simple question. So where do we go from here?
Good question.
That's a good question. Well, I think in phase 3, I can tell you where we're going in phase 3. So in phase 3, we are already looking at improving the models, so staying at the same resolution but trying to improve the models. But we are also using this huge data set that we have to train climate emulators. Because as you know, as you probably have seen with AI, inference is orders of magnitude faster than a normal forecast. So we're hoping that we could augment further by training these climate models to learn on this very rich data set and be able to run even more of these projections and ensembles of these projections so that we can better capture the uncertainty. And hopefully that will help us to push the boundaries further. But then at the end, it falls down to each and every one of us to do our part as well. So we provide the data. The data is now on the Destination Earth platform. Everybody from Europe can sign up. They can spin up their Jupyter notebooks. They can start looking at their own areas at different fields and variables. And I think then we can, do it in our local communities, maybe pressure our own representatives to take actions on this and be better informed and move forward to this. It was philosophical in the end, I'm sorry, but maybe it was just technical, the question.
It's a good time to be philosophical in 2026, I guess. There was one online question, is this software public?
Yes. Not the models. I mean, some of the models, Icon is open source. IFS, we've just open sourced OpenIFS, which is based on exactly the same cycle that we've run the simulations. So yes, you can go on GitHub and clone it and run it. The digital twin engine is all based on open source software. So everything that you see there, EarthKit, Multi-O, Polytope, everything is open source. So yes, the software is open source. And the data, if you're in Europe, you can sign up and you can have access to the data.
Any more questions? I have one, which is, so far this was like a very refreshing session, talk about like physical modeling again, finally. And kind of scaled to like really, like the old way, basically scaled to big machine, right? I mean, how is this going to change? How much machine learning is going to creep into those model simulations? You already said that we will have those models also for data set generation, so they're definitely not independent of machine learning. But how we perform those models? Is there going to be a creep in of machine learning somewhere?
Well, I think they can both live together, and they should. I think with the physical models, you have a better understanding of the physical system that it models, and with AI, you just have the super fast inference, so you can generate a lot more data and a lot more ensembles. So I think we need to unify this so that we can just, our goal also at ECMWF, is just to get the best forecasting system out. Whatever that is, it has to be the best forecast. And I think the same we try to do with the climate DT. We have to be open-minded and try and explore. It's a research project, and then just pick the best. Yeah.
Okay, thanks a lot.
Thank you.
No more questions here. Thanks a lot to Ioan.